God damn it!
Focus, damn you. Yeah, mine's not focusing.
Expletive deleted.
That was in our living room.
Yep. Happy Christmas.
Yeah.
The neighbors are probably gonna call the cops.
I feel like we should put it out.
No, it'll burn out.
We'll light our house on fire.
No.
Not even with the raining, burning ash.
No.
Stand over here.
So what you just witnessed was the Donahue tradition of setting the Christmas tree on fire after New Year's. This one we actually didn't get till like February, so it was nice and dry. So the question is, where did that energy come from? So we obviously set it on fire, which is a chemical reaction. But why was it giving off energy? Why do chemical reactions give off energy? So we'll be talking about that. And there's a word for that. We call it enthalpy, and it has to do with energy and reactions. So things that we're trying to accomplish in this video is describe what happens in terms of energies as bonds are broken and new ones are made, as well as use table I to determine if a reaction is exothermic, giving off energy, or endothermic, where it's absorbing energy, and include energy in the chemical equation itself, as well as being able to draw and label potential energy diagrams and label things like activation energy, heat of products, heat of reactants, the change in heat, so on and so forth. So the thing about this, the tree has energy, right? And it has these chemical bonds. Here's just an example. We got H2 and we have I2 as our examples over here. Oh crap. H2 and I2. So if we're going to get these to react, the first thing that we got to do is we got to break the bonds that are holding those atoms together. So that takes some energy. We need to invest some energy in order to break those bonds. Right? So we're adding some energy to it, we're weakening those bonds, and then we're going to break those bonds, right? The H's are going to break apart. So in order to do that, we started at some energy. All right, so let me label my axes potential energy, and then this is just time. What happens to the potential energy over time? So we started with a certain amount of energy, and we had to put some in order to get the reaction to occur. So we put energy in, broke the bonds. Now what's going to happen is that we can make new bonds, right? Those two things can come together, and when they do that, they're going to release energy. Now it depends, where is this going to end up? It's going to go down, but how far down is it going to go? Is it going to stay up high, or is it going to go down even further, releasing more energy than we put in? And that is going to be determined by looking at table I. So if we look at table I, this right here is our delta H. It's saying that it was a positive change in energy, meaning that overall there was a gain in energy in this stuff. So we're going to end up higher than where we started. So again, we started down here. We had to invest some energy to break those chemical bonds that were holding the things together. And then once we got them to react, they're going to start releasing energy when new bonds are made. So breaking bonds takes energy. And making bonds releases. Now what happens overall is dependent on how much energy you need to put in versus how much energy you got out. So for this example, we had to put in energy, right? So it's kind of like magnets. We got two different magnets being bonded together right now. First I have to break that bond, so I got to invest some energy, and you can hear that energy being released when it comes back together. Same thing over here. Two different magnets, certain amount of energy holding them together, got to break it apart. Now if I want to do a switcheroo, I got to invest that energy to break those bonds between those two magnets. And now when the magnets come together with their new partner, they release a certain amount of energy as well. Some of them release a lot more energy than others. If you take a look, the small red and blue magnets have a lot of energy, enough that they can pull them straight across. So we want to take a look at the energy before and then the energy after to tell us how the energy changed overall, right? So here's a potential energy diagram. Let's say for the lighting of the Christmas tree, right? We had to start it with a lighter. We had to invest some energy. And then once we got it to react, it started to lose that energy. Now my question is to you guys, did it lose more energy than we put in, or did it gain energy from the environment? Hopefully this one's pretty obvious. The tree released a bunch more energy than we put in, so it's going to release more energy than we had to put in, and it's going to end up with lower energy than what we started with. So where we started, we call that the heat of reactants, because that's how much heat our reactants start with, and we abbreviate it HR, heat of reactants. Where we end up, if you had to take a wild guess, we call that the heat of products. And take a guess how we can abbreviate that, HP. Now if we were to draw an imaginary line, and I think I can change my colors here, so I'm going to do that. We were to draw an imaginary line going across from the heat of reactants to the heat of products. This right here, from where we started to where we finished, we call that the change in heat, or our delta H. If it's a positive delta H, then it's endothermic. And if it's a negative, then it's exothermic. And you can see here we lost energy, right? We went down, so it's a negative change. So this would be an exothermic reaction, the burning of the Christmas tree. Now there's also a certain amount of energy it takes to get the reaction to start, right? So if we're starting right here, we had to invest this much energy to get it to react. And we call that the activation energy. Not really the most creative name, but it is descriptive. It's how much energy it takes to activate it. And we call that, or abbreviate it, big E, little a, the activation energy. How much do we got to put in order to get it to react? All right, so yeah, that's what's going on here. So let's take a look at something if it was an endothermic reaction. Let me just quickly erase all this. So if it was an endothermic reaction, we start at a certain amount of energy, we invest a bunch of energy, and we end up higher than where we started. So let's label this again. Let me change my pink color to a blue. Blue sounds good. So again, right here, that is what we started at. So that is our heat of reactants. Where we end up is going to be the heat of our products, because that's the heat, how much heat our products have. The change between the reactants and the products is still going to be the delta H. For this, it's a positive value, which means that it's endothermic. All right, and then this right here, well, what is our activation energy? We had to go from all the way down here to all the way up here. So this right here is our activation energy. All right, it's more than the delta H, because we had to put in more energy to get it going, and once it's going, it held on to some of that energy and didn't release all of it. So that would be an endothermic potential energy diagram. Now, table I has a bunch of different chemical reactions, and it lists the delta H for each of these reactions right here. Right, it says delta H, what it is, and if you look at the very bottom, you may forget, which one's endothermic, which one's exothermic. I don't remember. At the very bottom of that table, it tells you. It says the delta H values are based on molar quantities represented in equations. A minus sign indicates exothermic. So exo is negative, and if it's positive, then it's endothermic. So if we take a look at these examples, they're all exothermic because they all have negative delta H's. Whereas if we look at some other places in the chart, like these examples, they're positive. So these would be endothermic reactions, because they have a positive delta H. All right. So now the question becomes well, all right, endothermic means we're adding energy. If I were to include energy into the equation, where would I put it? Well, if we're adding energy, then it's a reactant. So if this is my reaction, KNO3 plus water, I'm dissolving this stuff, giving me the ions, has a positive delta H. That means I had to invest energy. So I'm really saying KNO3 solid, plus that much energy, 34.89 kilojoules, will then become a K plus ion in solution and an NO3 minus ion in solution as well. So endothermic, it goes to the reactants. Here we have an exothermic reaction, meaning it's giving off energy. So energy is a product of this reaction. It's being given off, you end up with it. So if I had to rewrite this, it would be, C3H8 plus 5O2. So this is propane reacting with water, or I'm sorry, oxygen. It's burning to give us 3CO2, 4H2O, and a positive 2219.2 kilojoules. You may be asking, Mr. Johnny, at this point, but it says negative there. Why don't I put a minus there? The minus is just telling you that it's a product, that you're losing that energy. Where does the energy end up? It ends up in the product side as a positive thing. Here, the positive sign is telling you that you needed to invest it. It was a reactant, so the 34.89 kilojoules is on the left side, but it's always positive. You'll never say, like, subtract this energy and then you'll have a reaction. No. You'll always put a positive. The sign from the delta H is telling you just which side it goes on. All right, so that's it. Keep watching the video. I'll burn some more things because I'm a pyro. What are you going to do?
Are you willing to be had? Are you cool with just an eye? Is it just